Okay, we're back again. We're going to talk about motion in one dimension. The last couple videos in this sequence, we looked at defining some of the basic quantities we need in order to describe motion, position and time, and how when we look at how those change, those give us to definitions for other quantities, like displacement, the difference between positions, and velocity, the rate of change of position with respect to time. And we said we could look at that at an instant, where it's the slope of a position versus time curve at a single point, or we can look at the average across a range of time, where it's the displacement, the change in position, divided by the change in time. And we also said, we care about the types of different quantities that are out there. Things where we care about the direction are vectors that have size and direction to them, such as velocity, position, and displacement, and things that don't have a direction assigned to them other than, say, a positive or negative value would be something like time, or perhaps mass, or volume. But now I want to take a look at situations where velocity changes. So let's imagine a situation. Let's describe this here. And I want us to solve a very simple problem and graph what's going on with it alongside. So I'm going to make a graph here showing velocity. And I'm going to call this velocity in miles per hour. And I'm going to use time in hours. And let's do this 0.5, 1.5. Okay. Okay, so what I want to do is say this. And to make this stay velocity and not just speed, let's say that this is east. So, situation will be this. Let's say that we are traveling and we start off our original speed, our initial velocity, rather, is going to be 30 miles an hour. And we're going to travel at that velocity, east, we're going to start at rest. We're going to start rather at zero position. And we're going to go some position we haven't decided yet. But the change in time we're going to do for that is going to be half an hour. We're going to spend half an hour driving at that velocity, 30 miles per hour east. Okay. So this is a pretty straightforward question. And some things I'm doing to solve it, though, I'm modeling problem-solving techniques for a simple problem because they're going to become more complicated later. We want to have these strategies down. So this is a problem you might have seen in middle school, this sort of thing. But I'm assigning the algebraic variables to it. And we want to, I've assigned the numbers that go along with those variables. And I want to ask myself, what sort of situation is this? What's the relevant physics to this problem? And in this case, we're going at a constant velocity. And I know that when we're going at a constant velocity, then this equation for average velocity is true. This relationship between the quantities we know and the quantities we want to find out is true for when we're working with average velocity. And so that's the equation we get to use. And so we go ahead and start off and say, all right, so velocity v1 in this case is change in position over change in time. Let's go ahead and say that we're trying to find the change in position 1. Change in position 1, change in time 1. We want to know what change in position is, so we do our algebra. Multiply both sides by change in time 1. Cancel. And we get change in position is velocity times change in time. And I know perhaps you did all of that in your head without writing it down. But a good problem-solving strategy is to identify what the relevant physics is, see what tools describe that physics, what are the equations that work with that physics, bring those in, and now we're solving the algebra symbolically first before we've dumped any of these numbers in. Now maybe you're quick enough at math that you've already solved it a while back in your head or on a calculator, but we're doing it this way anyway to develop the good habits. It's also a bit easier to catch errors this way. So we've got 30 miles per hour and a half hour, 0.5 hours. Hours divide by hours to equal 1. So the hours go away. 0.5 times 30 gives us 15. Units of miles are left over. Okay, 15 miles. Okay. So that's fine. Now, let's graph that on our graph here. So let's go ahead and mark this as being, let's see, give ourselves a little more space here. Call that 30. And we were plotting that motion on the graph. It would just be this horizontal looking line here. A line that's parallel to the time axis. It's staying the same velocity the whole time. What I want to do now is I want to drop a line down here, and I want to find the area of this rectangle. And so, okay, I know areas. This is also very, elementary school. So the area of a rectangle is length times width. So that's length is 30. It's not just 30, it's got units on this axis. So 30 miles per hour. And the width is 0.5. It also has units. We need those. 0.5 hours. That's the same math we did down here. So that area is also equal to 15 miles. Okay. So think about this for a sec. So it's kind of like anytime you're multiplying two things together, it's like you're finding the area of a rectangle where those two things are their sides. Okay, let's do another. Let's do something attached to this. So we want to change the velocity. So let's do that. Let me give us a little bit more space and say that in the second leg of the trip, we get on the highway, we continue to go east, but now we're going to go at 60 miles an hour. Mark that up here. And now we're going to spend a whole hour doing that. And we want to know how far do we travel during that time. And so we say, okay, well, this is the same type of problem as before. It's still constant velocity. That equation still works. The math here is all the same. We just have to change the numbers. Since we did this symbolically with algebra before, then we can basically start from here and say delta x2 equals v2 delta t2. So that's 60 miles per hour times 1 hour, and that's 60 miles. And if we plot that on our graph, and find the area under that rectangle, what do we think happens? Well, the width here is still 1 hour, and our velocity is 60 miles per hour. So when we multiply the two of them together, it's the same math as before, and the area underneath that box was that displacement. So we see a pattern. Okay, and then the area, the total distance we traveled from when we left to the end of those 1.5 hours are these two distances added together, so 75 miles. The total area of these two rectangles added together, also 75 miles. That displacement is the same as the area underneath that velocity versus time curve. Wait a sec. So all right, step back. So if we did this and we have velocity and time here, this is like east to, I don't know, miles per hour, this is hours, and we're cruising along here, and let's say instead our graph looks, we're changing our velocity. So we'll start up with rest, and then we're changing around our velocity as time goes by. And that's not rectangles. You can't go from instantly from 0 to 30 or 30 to 60 without going through all the speeds in between for at least some infinitesimal amount of time. It has to change. So, well, how do we get distances and areas? Well, okay, so if we chop this up into strips, and made those changes in time small, then the differences in the areas between those rectangles and what's under the curve could be small-ish. If we made those narrower and narrower, then it would be a lot closer to the area underneath the whole curve. So what we imagine then is that, okay, this displacement is the area under a velocity versus time curve, and we say that it's the sum of all of these rectangles added together, but they're not regular rectangles. Just like we had to make the slope, where the rise and the run were infinitesimal changes, we've got to make these strips of time infinitesimal. So we have to do the sum of all the different velocities times the infinitesimal changes of their times for which they have those velocities. Well, that's the notation we use to represent that. Only this long s, we call it integral sign, because if we're doing this for curves, the mathematics required to do this is called integral calculus. These are both, that and the differential calculus are parts of the calculus of infinitesimals. Should have been sharper there. Okay. Just there. Okay. Anyway, I think that's where we should stop for now. And we're going to work with this and changing velocity a little bit more in the next